Hello, and welcome to this video workshop presented by Macnica Americas. This presentation will acquaint you with the Broadcom WICED Smart SDK. I'm Troy Jones, a member of the technical staff here at Macnica Americas, and I'll be leading you through this second vWorkshop in our IoT series. Now, wouldn't it be cool if you could create your own product? Let's say a heart rate monitor you could use to sell to the masses. Well, after watching this workshop, you'll be able to do just that. I will show you how you can create a custom Bluetooth low-energy device using Broadcom's Bluetooth Smart Silicon and the WICED Smart SDK. The primary goal of this workshop is to acquaint you with the Broadcom WICED Smart SDK, a complete environment enabling application development for a Bluetooth smart device. We will first review some of the details of Bluetooth Smart that were covered in the first IoT workshop. If you missed that workshop, it is available for immediate viewing via the Macnica Americas vWorkshop landing page. We will start into the meat of this workshop by discovering the basic features of the SDK. In order to understand how the SDK can be leveraged to your advantage, we will need a better understanding of the building blocks that make up a BLE application. From there, we will run and debug an existing application on the Impression Odyssey Bluetooth Smart Sensor Development Kit. We will wrap up by uncovering the many beneficial Broadcom and Macnica resources at your disposal. Let's get started by reviewing what Bluetooth Low Energy is. First off, remember that Bluetooth Low Energy is commonly referred to as BLE and is also known as Bluetooth Smart. From a physical standpoint, the technology operates in the 2.4 GHz ISM band and has a theoretical bandwidth of 1 megabit per second. In reality, you'll see data rates around 300 kilobits per second. The system is based on a client-server model and is controlled by a basic one-hot state machine. The client, perhaps a smartphone app, wants to access data that is being offered by a server, the BLE device in our case. A peripheral device will advertise itself while a scanning central is looking for one. Once the two see each other and are initialized, defining their roles, they enter the connection state where data is transferred between the two. The data that is available for a given BLE device is defined in a device profile. This profile is comprised of services, and the services are made up of characteristics. Each characteristic contains a value. That's the real data that we want access to. The other optional descriptors for these values are within the profile as well. Recall that the profile, as I just described, is maintained in a database within the application code structure. This is known as the GATT database. As defined by the Bluetooth spec, and is expanded upon by the low energy section, a BLE device must have a generic access profile service and a generic attribute profile service. The additional optional services that are defined in your device's profile will define the nature of your BLE device. Is it a heart rate monitor, a key fob with proximity detection, or perhaps a timekeeping device of some sort? Many common device profiles are defined by the Bluetooth SIG and are available via the Broadcom Community Developers site. And finally, for our review, recall that all the data and connection details for the BLE are handled via the BLE stack. All information headed up from the lowest physical layer or moving down from the application layer must adhere to the data structures as defined by the specification. Keep in mind that the Broadcom 2073X family of devices include the above stack in ROM, and this is ideal when developing a new peripheral device. This allows you to concentrate on the top layer application and how you are going to create the next awesome jaw-dropping Bluetooth low energy device that is going to take the market by storm. Okay, now that we are back up to speed on what BLE is and how your application is going to play in all this, let's dig into the Broadcom WICED Smart SDK. What is this WICED Smart SDK? Well, in a nutshell, it is everything you need to develop BLE applications targeting a Broadcom Bluetooth Smart device. It includes a compiler, a build engine, debug hooks, IP, and examples, all in an integrated development environment. The IDE is Eclipse-based, which is the latest open-source de facto standard for build environments. Broadcom provides all the necessary source code, headers, makefiles, patches, etc. to build applications targeting the Broadcom BCM 20736 and the BCM 20737 BLE devices. They have made this IDE so simple, you can literally compile and download your application to your custom BLE device with a trivial one-button click of your mouse. It has great host platform support and is free to download once you register on the Broadcom WICED community site. The SDK allows you to develop applications for BLE devices that can be a master and a slave at the same time. See the Hello Client and Hello Sensor sample applications as reference. Some of the more notable features of the SDK are the Smart Designer, the Trace Viewer, and the predefined debug configurations. The Smart Designer is a wizard that helps you define the profile, the services, characteristics, values, and descriptors of your custom BLE device. This wizard takes GUI input and generates source code for your application. The details of this wizard will be more thoroughly explored in the third IoT workshop entitled Build Your Own BLE Device. The Trace Viewer is an integrated serial console that is used to capture trace debug information that is coded into your application by use of printf-like function calls. I will demonstrate this capability later on in this workshop. Also, for those of you that are in need of a deeper level of debug, the SDK provides predefined debug configurations that take advantage of the serial wire debug capabilities of the Broadcom BLE devices. Take note, the serial wire debug capabilities are not enabled on the modules, only on the BLE SoC chips. Probably the most beneficial feature included in the SDK is all the sample applications. You can see here, there are 30 applications provided to you with the default SDK install. All these applications can be run on the Broadcom BLE devices out of the box. The only real dependency on the application to provide real data would be which development board you use it on. I'll cover the options you have for development hardware in a moment. It is worth noting that all these applications take advantage of using the Bluetooth SIG defined profiles as a starting point where applicable. All source code for these applications is provided in clear text and is very easy to copy and paste the application that most closely matches your needs so you can start from known good source. Here is a static screenshot of the SDK. It has 4 main functional areas. First, the Project Explorer on the left encompasses SDK projects. The 30 applications you just saw are under the WICED Smart SDK project. This is where any additional projects you create or import will be displayed. The Impression Odyssey project will be one such project you will import once you receive your Odyssey kit. All the API documentation is also online within the SDK under the DOC folder under the WICED Smart SDK project in this tab. Next, the editor window is present front and center. As with any decent IDE, the text editor is context sensitive and can be personalized per Eclipse menu options. The magic of the SDK is launched via the Make targets in the upper right-hand window. Here, each application build target is defined and can be executed with a one-button mouse click. I will be covering the details of how these Make targets are used in a minute. Finally, at the bottom of the IDE is your console window. As expected, all build status messages and errors are presented here. This is also the area in which trace messages will appear during debug sessions. Let's take a look at the SDK live. You will launch the WICED Smart SDK IDE via a standard shortcut for your operating system of choice. Once the IDE opens, the default layout is just as I previously showed you. In the upper left corner, you will find the Project Explorer with the pre-populated WICED Smart SDK project. Upon opening the project, you will see all the folders that contain everything you need to develop a Broadcom Bluetooth Smart application. Within the Apps folder, you can find the 30 clear text example applications that can be run out of the box. For example, here is the Hello Sensor application and the C source and header file along with a make file that define the application. We will look at the details of this source in the next demo. Let's just stick to the basic functionality of the tool for right now. Probably one of the most important folders in the included SDK is the Doc folder. Simply double-click the API HTML document. Here you can access the API User's Guide, where you can find the definitions and descriptions of all the WICED functions, as well as several very useful app notes, including the Quick Start Guide and the fundamentals of how to write a WICED Smart application. The other included folders contain items such as the necessary header files that encompass the SDK, the platform-specific helper files for the 736 and the 737 devices, all the behind-scenes tools such as the compiler and scripts are located in the Tools folder, and finally, all the necessary files that enable the BLE stack interaction are in the WICED Smart folder. The top-level makefile that pulls all this magic together can be seen at the root level, here. That's the basic makeup of the WICED Smart SDK project. Let's now look at the editor capabilities of the IDE. We'll open the hellosensor.c file. As discussed earlier, the center window is used as the editor. Right off the bat, you can see that the editor is context sensitive and has many useful features built into it. For example, on any element within the source, let's say this bleprofile.h header file, simply highlight the element and press F3. This fires off the built-in feature of Eclipse to locate and open the declaration of the selected element. This is extremely helpful when trying to write code that rides on top of a very complex protocol stack. Another cool feature is the fact that the editor not only understands comment syntax, but it also can parse your ifdef compiler predirectives. Seen here, OOB pairing and passkey pairing are not defined, and the source code is highlighted so that you can see that easily. Okay, now let's move to the heart and soul of the WICED Smart SDK, the Make Target section. Here you will see a pre-populated list of targets that allow you to point and click a single line to compile and download your code to your target BLE device. There are help and clean targets as well. Running the help target, we can see a list of all possible make target objects and options. We see here the necessary order of parameters. First, the target, which is the application to be compiled, then the object, be that to download or just to build, followed by any number of options you may want to use. I will now run the make target to download the Hello Sensor app to the target BLE device. In the console window, you will observe the code compilation and the linking and creation of the executable. That is followed by useful information about the code size and any patches that are applied. Then finally, we can see where the script to detect a BLE device is run so that the code can be downloaded. Well, in this case, we failed out since I did not have a target board connected to my host. I'll be showing you a successful download after a bit. So that's it, a straightforward, fully functional IDE. Okay, now that we have seen how the SDK pulls together the basic pieces of a development environment, let's take a look at the individual parts of a BLE device application. Let's start by getting a better understanding of the role of the GATT database and the values that are defined for each characteristic within each service. Keep in mind that the GATT database is simply a shared data structure that can be accessed by both the client and the server. There are 4 methods to transfer data between the client and the server application. The first 2 operations, read and write, are requested by the client and the server responds to those requests. These are used to access values stored in the GATT database directly. Since the database is a shared resource, data is not sent directly to the device application, it is simply written to the database. In order for the application to access the new data, the methodology of callbacks is used. The second two operations are notify and indicate. These are enabled by the client, but initiated by the server, providing a way to push data to the client. Indications are acknowledged and notifications are unacknowledged, making them faster but less reliable. What this means is that the application on the server side will generate a notification to the client to let it know that the new data is available and that the data is actually part of the notification. For example, let's look at a heart rate monitor. The current heart rate is constantly being read by a sensor on the BLE device. That heart rate is then populated into the GAT database in the appropriate characteristic value for the heart rate service. At this point, how does the client, let's say a phone application, know that there is a new heart rate value available? Well, a few different methods could be employed. Perhaps the client can be designed in such a way that it just periodically reads the heart rate value from the GAT database on its own terms. Well, this is a brute force way and is not really efficient. Another common method would be to embed the data within a notification. This notification is the most direct and efficient in terms of resource utilization and time in exchanging information between the server and the client. The server will create a notification message with the updated heart rate value and push this to the client application. Once the client has the new value, it can do with it as it pleases. For example, update the data displayed to the user. A callback, to be more specific in computer programming, is a piece of executable code that is passed as an argument to another piece of code, which is expected to call back or execute the argument at some convenient time. The invocation may be immediate, as in a synchronous callback, or it might happen at a later time, as in an asynchronous callback. Here is a list of callbacks that an application can register upon initialization. This list is fairly intuitive and provides for all necessary communication between the client and the server. With our newly gained understanding of how a BLE device application and a client will communicate with one another, what are the specific parts of the device application? Recall that the Broadcom smart devices utilize internal ROM to execute the BLE stack layers. Now, the device must be properly initialized at power-up so that this ROM-based code will function properly and handle almost all of the communication and data transfers without the application having to be explicitly involved. For every Broadcom Smart application, there are a few components that must exist in each application. Alright, number one, by Bluetooth definition, the application server must host a GAT database. As we now understand, this is where all the real data is stored via a shared resource. Number two, for the Broadcom BLE devices specifically, we must define the device configuration. This will include basic information such as advertising data, device name, timer intervals, etc. Number three, the UART configuration will define baud rate and pins, and the GPIO configuration will be set up so that the lower levels of the stack know how to interact with the outside world. Number four, the stack must be notified of where the device configurations are and what the main entry point of the application will be. Number five, once the main code is called via the create function, the device will be initialized and the application will start running. And finally, number six, part of the responsibility of the create function is to register any and all callbacks that will be used to handle events as they happen. Let's take a look at some real code to help us understand each of the above items. As mentioned, as required by the Bluetooth LE spec, the GAP and GAT services must be defined in the GAT database. They are not shown here in this code snippet. The code seen here is the heart rate service profile comprised of the service, two characteristics, and a single descriptor for the first characteristic. Notice that each of these entries is actually a macro, highlighted in red. These macros are defined in bleprofile.h, a header file that is included as part of the Broadcom WICED Smart SDK install. Each of the parameters within the macro are typically defined within the application codespace and are values defined by the Bluetooth SIG. Next in our list of required elements is the Broadcom Smart Device configuration. This is an extensive configuration construct that is comprised of about 43 separate items. Everything from defining the timing intervals, the advertising details, the power save timeouts, and how an LED or a buzzer might be used are configured. You can look at any one of the included BLE apps that are part of the SDK install to see a complete list of configuration items. We'll explore this a little later in this workshop as well. The next item that needs to be configured is the peripheral UART. This is a pretty basic configuration in that all that needs to be set up is the baud rate and the GPIO pins on which the peripheral UART communicates. This is typically done with either explicit values or by use of macros, as seen in the cycling speed and hello sensor examples. In this configuration construct, the GPIO pins that will be used on the BLE device are configured to function on the device pin defined by the macro. These GPIO connections will depend on how your BLE device, once designed, will be physically hooked up. The example here is for the Broadcom Tag 3 board and the Hello Sensor applications. We can see that the application will be using non-volatile RAM, a push button, LED, the battery, and a buzzer, each connected to a different GPIO pin on the BLE device. Upon reset, the stack will look for the required function application_init. This is where pointers to the data structures that define the device configuration, as we just talked about, will be made available to the stack, as well as information about what the name of the actual entry point into the application is. In this snippet, we can see that the application entry point will be BLECSC_create. So, what needs to be in the creation of an application? Fundamentally, the profile will be initialized, the GPIO initialized, and the database will be set up as well. After those items are taken care of, the application will register any event callback function it wants to be notified of. We will talk about this on the next slide. Finally, the code typically starts the timers and moves the BLE device into the advertising state from the idle state, and away you go. The application is now waiting to be triggered by any of a number of registered callback functions to handle data accordingly and switch states if necessary. Now, these callbacks, they really are the lifeblood of your BLE device application. Anytime something happens, one of these callbacks will execute to process the relevant data. This could be handling a loss of connection gracefully via the connection down callback, or maybe a counter's expired and you need to take another temperature measurement and notify the client app that there's an updated value to read. These callbacks may force a transition into another state as well. As you create your own Bluetooth smart device, you will spend quite a bit of your time choosing what callbacks you'll want to utilize, then coding and debugging these callbacks for your needs. Let's take a look at some of the details of the actual Hello Sensor application to get a better feel for how all these pieces and parts are stitched together. The source is included as one of the 30 reference applications provided with the default install of the Broadcom WICED Smart SDK. I chose this application as a demonstration piece as it is fairly straightforward and all the parts we just covered are encompassed within a single matched C source and header file, hellosensor.c and hellosensor.h. The source files also pull in a few of the Broadcom SDK platform-specific and device driver files as needed for proper stack interaction. I'll show you the GATT database with the services and characteristics defined, and then I'll show you where the BLE device configuration is and all the options that need to be set. This is followed by the peripheral UART and the GPIO configuration sections. Next, we'll look at the application initialization code that registers the callbacks, and then I'll point out where the timers are kicked off and a tweak to the advertising data is made. Finally, I'll show you where the advertising actually begins. Here, I have the hellosensor.c source file open in the IDE editor. The first thing of interest is the included header files. You can see there are a couple of BLE stack specific headers followed by a GPIO driver header file that defines functions to access general-purpose I/O ports of the Broadcom Bluetooth smart devices. Next are a couple of standard C inclusions, and then the platform header that is used when targeting the Broadcom tag boards. The hellosensor.h file encompasses the values of such items as the UUIDs used, as well as other application-specific definitions and prototypes. The final included header pulls in stackable patch and application runtime utilities. The first set of constants declared by means of pound defines are seen here. We set up the NVRAM memory block that will be used, and then the UUIDs for the custom service that is used for this application. See here the Hello Service 120-bit UUID defined, followed by the two 128-bit characteristics. Recall that SIG-defined UUIDs are 16 bits in length, and that custom ones are 128 bits. The conditional constants for out-of-band and passkey pairing are defined here. Next, the structure of the NVRAM storage is defined. In this application, the bonded host address, the client configuration, and a value defining a number of LED blinks will all be stored in NVRAM. Now this is where the source code starts to get juicy. We see here where all of our function prototypes are declared. A few of these should look somewhat familiar and in line with what we just recently discussed. The create function here, along with a few of the obvious callbacks like the connection up and connection down. Now, here is the infamous GATT database that I have talked so much about. The required GATT service is declared here. There are no characteristics associated with this service. Next, we see the required GAP service and its two characteristics. Notice the macro used to declare the GATT and GAP services, as well as the associated characteristics, are all 16-bit. Following the two required services are the optional services for this application. Our first optional service is the Hello Sensor service, which encompasses two characteristics: a 7-byte read-only notification value and a 1-byte writable configuration value. There's also a 2-byte descriptor that is a standard GATT characteristic descriptor used by the client to enable notifications or indications. The next optional service is a standard service, meaning it's defined by the SIG, which is the device info service. Here we can see three 8-byte read-only characteristics defined as Broadcom, then 123400000, and then 8 hex values, respectively. The final service we declare for this Hello Sensor application is another SIG-defined service, the battery service. There is a single 1-byte read-only characteristic defined. Okay, moving on. Our next construct of interest is the BLE device configuration. This is the structure that holds the 40 or so values that define how the Broadcom Bluetooth smart device will behave. The type definition of this structure can be seen in the BLE_profile.h header file. A quick look shows us that items such as the timer interval and the default advertising mode are defined. Deeper into the configuration, you can see that items such as LED blinking styles and durations are defined too. Following the device configuration are the peripheral UART and GPIO configuration constants. These type defs can also be found in the BLE profile header. We see that the UART will be defined to run at a baud rate of 115,200, and the pins are disabled and defined by macros. The peripheral UART is disabled here because we will be using the UART that communicates over the host controller interface. Next, we see where the Hello Sensor application defines the GPIO configuration. We see that the write protect pin for the NVRAM is used, along with pins for the push button, LED, battery, and buzzer. The remaining available GPIOs are unused and excluded with a -1. The following set of macros define flags that are needed as part of the GPIO configuration. Now, it's beyond the scope of this workshop to dig into the details behind this configuration structure, but I will be spending quite a bit of time covering this subject in the next IoT workshop, Build Your Own BLE Device. Here are a few global variable declarations with their initial values set. Now, for some executable code. As required by the Broadcom implementation of the BLE stack, the application_init function is here. Recall, this function is responsible for notifying the stack of the location of the database and configurations we just explored. It is also responsible for telling the stack the name of the function that is the entry point for this device application. In this case, it's hello_sensor_create. Let's take a closer look at that entry point function. I'll point out the critical tasks that the create function must do. The first thing to note is in the initialization of the BLE device using the device configuration. Recall, this is the structure that defined the timer interval, LED usage, etc. Next is the initialization of the GPIO using the GPIO configuration structure. Following that is a call to a custom function named database_init. Scrolling down in the code, we find this function which simply calls the function to initialize the battery monitor. Now, it's important to understand where this BLE bat_init routine lives. It's already in the ROM on the Broadcom BLE chips. Recall from the IoT One workshop that many standard Bluetooth applications and utilities are pre-populated for your use in the ROM. How very convenient. Okay, back to the create function. After all the configurations are initialized, along with any ROM code you choose to use, you now need to register all the callback functions you plan to use. Here we can see that the connection up and connection down events are connected to the hello sensor connection up and down functions respectively. We also see that the advertising timeout event is registered to the hello sensor advertising stopped callback. Let's take a quick look at the connection up callback. We see that upon entry to this callback, we access the connection handle and then save off the address of the connected device and print it out using trace capabilities. Next, advertising is turned off so that no other scanning device will see us and the idle timer is then started. The callback function then looks at the configuration and determines that since encryption is required, no notification will be sent to the master until it is bonded. If we have never been bonded, a call to the security manager is made. Now once bonded, the bonded device address is stored in the NVRAM for faster future connections. Finally, the connection up callback will call the encryption changed function to take the next step where the LED will be blinked and the buzzer sounded. Let's go back to the callback registrations. This next section of code is not used as the OOB pairing and passkey pairing capabilities are not enabled for the hello sensor application. There are several other callbacks registered here. They include encryption change, bond result, client write, the interrupt handler, and finally the timer timeout. After all the callbacks are registered, it's time to get things going. First thing is to start the timer so the device can respond in a timely manner according to its configuration. This entire section here is simply modifying the advertising PDU and creating the actual advertising data. Once the create function has done all its initialization, callback registering, and packet manipulation, it directs the device to start advertising and we're off and running. At this point, any scanning device will be able to discover our hello sensor BLE device and initiate a connection. Now, as you can see, there are many macros, parameters, device UART, and GPIO configuration settings that need to be set in defining a given BLE device application. But have no fear, you will not need to be creating this by hand. As mentioned during my detailing of the features of the SDK, there is the Wicked Smart Designer wizard. This wizard is used to create this exact code for you dependent on your GUI inputs. I'll be going over the details and how to use the wizard in the third IoT workshop coming soon. Up to this point, we've seen what is needed to create a BLE device application and some real code that creates these parts. Now, let's actually get one to run. Recall the Make Target section of the SDK I mentioned before? Well, these are the point-and-click commands that allow you to very easily compile, download, and debug an application. There are several make targets defined, but the ones you will use most often are clean, build, download, and recover. You can set up the target to help to see a full list. The syntax of the make targets is critical. I say again, critical. There are three main parts to the character string. The first part calls out the application by name, which is the same as the folder that encompasses all the source files. The second part will define the Broadcom device, either the 20736 or the 20737. The last part directs the makefile target to be executed. Additional options can be specified for debug and directed UART output, or even specifying the address you want the BLE device to use. Hooking up your development board is trivial. Both power and communications are provided by a single USB cable. The dev board has an onboard micro that is responsible for translating the UART communications from the BLE device to the USB port on your PC. You can see which serial COM is being assigned to the USB port by looking at your device manager on Windows or similar utility on a Mac or Linux. The scripts that are run by the make target will automatically parse through all COM ports on your PC until it finds a responding BLE device. If you have multiple dev kits connected or need to specify exactly which COM port is to be used, simply add UART equals COM X to the end of the make target where X is the actual COM port number. Double-click the desired make target and the application is compiled, then download it to your device. Yeah, it is as simple as that. The BLE device application I'm going to demonstrate in a minute is the heart rate monitor running on the Impression Odyssey sensor kit. A while back, I mentioned a debug capability of the SDK called trace. This is a method by which you can debug a Broadcom BLE module by means of printf statements. To use trace, you simply enable the application to output trace messages to a UART via a global variable declaration. Messages can be output to either the peripheral UART or the UART of the host controller interface, which is the recommended method. The syntax is similar to that of the standard C library printf function. You can even print out formatted variables using parameters. To view the trace output within the SDK, you need to tell the tool which UART to capture the trace data from. Part of the Broadcom plugin to Eclipse for the WICED SDK is the Trace pull-down menu. From here, you can specify which UART you want to capture trace data on. This will be the same UART COM number that you can observe via the device manager on Windows, or it is optional to let the tool assume that your trace UART is the same UART used to download to the BLE device. As soon as you click on the Connect button, any trace messages you have chosen to use in your source code will appear in the console window at the bottom of the main SDK window. Cool. All that sounds good in theory. So let's actually do it. This is what my setup looks like. In this demo, I will compile and download a BLE heart rate monitor to the Odyssey Sensor Development Kit and use a third-party application to connect to the device and display my heart rate. With the device connected to a USB port on my Windows PC, we can see that the onboard microcontroller has established a serial communications link on COM27. We need to know this when we enable the trace messages later. In my WICED SDK IDE, I have imported an Impression project that includes the Impression Heart Rate Monitor Demonstration BLE application. We can see in the Make Targets section the clean and help targets, as well as a target for the Impression framework and the heart rate monitor. I am first going to run the clean target just to show you how simple it is and to start from a clean slate. The console window reports the status of the run. Back to the Make Targets. Now I will double-click the Impression heart rate target. You can see it is targeting the BCM920737 device. Again, the console window will show us all status messages. First, we see the source code compilation followed by the executable linking. We then get info on the application size, and immediately the make target runs the script to detect our BLE device and then downloads the application. On the Impression Odyssey board, the application will start once the BLE device is reset via a small push button, not the dip switch and reset button as directed here. These are messages intended for the Tag 3 board from Broadcom. Looking at my setup, I will instruct the smartphone app to start scanning for BLE devices, then reset the Odyssey so that the app moves into advertising mode. Immediately, we see the device pop up on the list of available devices that the app can communicate with. Now, before I pair the phone app to the Odyssey, let's turn on the trace messaging so we can observe some of the communications that are happening. I select the trace configuration icon and then select the COM port that we saw in the device manager for the Odyssey board, COM27. As soon as I click the connect button, all trace messages embedded in my source code will be displayed to the console window. Now, I will pair the phone with the device and away it goes. We see some initialization messages fly by, then the BLE app periodically notifies the phone app of the current heart rate. We can see it transition here from 0 to 72. Pretty cool, eh? Now that you're familiar enough with the SDK to become dangerous, where can you go for additional support? Well, the answer to that age-old question of, now what, lies in the Broadcom community. This is a web-based resource created by Broadcom early in 2014 specifically to support their WICED and Ethernet PHY and switch products. It has a substantial backing and is growing at an impressive rate. This is where developers will create an account and agree to a click-through license to gain access to the SDK, just as you've seen here, as well as countless resources of aid in taking your next steps into creating your own Broadcom smart device. It is very easy to get going. Simply register, download and install the WICED Smart SDK on a Windows PC, Mac, or Linux box. Once installed, you will see all the sample applications that you can use as a starting point for your own design. You can test out any of these applications on one of many development kits that I will discuss here shortly. Also, all the relevant documentation for the APIs as well as the application notes are part of the install to get your needs taken care of in short order. If what you need is not there, simply go to the community portal and quickly get what you are after there. The community website really does have all you need. Everything from app notes to board layout guidelines, blogs, and full functioning reference designs. The forums are very useful for posting and sharing support requests amongst fellow developers and Broadcom support engineers to shortcut your design needs. These forums are constantly being monitored by WICED experts to offer timely solutions to common issues. As for Bluetooth Low Energy kits, you have several options. Broadcom offers their Tag 3 that is 2737 SoC device-based. Note, this is not the 2737S module. With this kit, you can run every 2737 targeted BLE application that is installed as part of the SDK. And, just recently released by Broadcom, is the Sensor Eval module. This has an SoC device that is connected to several sensors including pressure, temperature, humidity. An accelerometer, gyro, and e-compass are also present. Again, many of the SDK default apps can be run on this eval system. Now, Impression's Odyssey Bluetooth Smart Sensor Kit is the perfect way to get started on your design journey. The Odyssey Bluetooth Smart Sensor Kit allows you to create a custom Bluetooth low-energy device in just minutes. It combines sensors for ambient and UV light, proximity, gesture, pulse rate, temperature and humidity, and acceleration. It is designed with a USB-enabled microcontroller and a Broadcom 2737S Bluetooth Smart module for connectivity. Here's a block diagram of the sensor board with the Broadcom module and associated sensors. You can easily increase the board's processing with an Altera Max 10 FPGA add-on board that also has Arduino expansion capabilities. An Mpression website lets you create a smartphone app to control your custom Bluetooth device in minutes without writing a single line of code. The app is built upon a framework that allows a user to choose a personality for the BLE device based on the available sensors. Once a personality is selected, the sensors are configured, and the FPGA is loaded, if applicable, and the appropriate control app is then loaded on the smartphone. The Mpression group has created a custom SDK project that includes the framework I just described. Within this framework, the fundamental BLE application pieces and parts are created in the main and BLE sources. From there, the capabilities of the GPIOs, I2C, and SPI buses, as well as debug capabilities and other miscellaneous functions, are clearly broken out into self-contained source files that you can use as needed for your system. In addition, Macnica provides a dedicated human resource to assist you in using the Odyssey BLE framework and designing with a Broadcom Bluetooth Smart device for your next Bluetooth Smart project. Register today as a priority customer and get the Mpression Odyssey Bluetooth Smart Sensor Kit at an introductory price of only $25. Coming soon, I'll show you how the Mpression Framework SDK project, along with the web-based smartphone app configuration tool, can be leveraged to create your own Bluetooth Smart device and interact with it. Beyond that, coming up in our next IoT vWorkshop, I will dig deeper into what is required to develop your own Bluetooth Smart device. We will explore in detail creating a custom GATT database, how to configure the device, the GPIOs, and utilize the UARTs that are available. Most of this will be done with the Broadcom WICED Smart Designer Wizard. We will also explore how the entire framework of the Odyssey can be leveraged to your advantage, including the customizable phone application. Thank you for watching this video workshop, and if you have any questions regarding any of the content you have seen today, feel free to send an email to workshophelp@macnica.com and include IoT2 vWorkshop in the subject line, and one of our Bluetooth Smart experts will promptly reply to your inquiry. I'm Troy Jones, and thank you again for watching, and look for our other IoT and Altera SoC on-demand workshops on the Macnica Americas website.